listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists. We're going to shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronics What's Up podcast. Today we're discussing the inner integrated circuit. It's better known as the I²C bus. That's a popular serial communication interface. It's mainly used to connect microcontrollers with peripheral ICs like sensors or even memory. The bus uses one bidirectional data line, SCL, and then one clock line, SDA, each. However, the I²C bus, it's not only used within circuit boards. This also extends into other areas in a bunch of different applications with the aid of various connectors and cables. This makes the I²C bus potentially more susceptible to external interference, such as ESD, bursts, and radiated RF disturbances. The goal of this podcast is to explain to the listener a suitable filter and protection circuit that increases the noise immunity of the I²C bus without sacrificing the signal quality of the data and the clock lines. For this purpose, simulation models were created in I²C, as well as a real application measured to verify the simulation results. The I²C operates according to the master-slave principle, whereby the master always initiates the data transfer. Due to its low complexity, the bus has achieved a wide distribution. However, the protocol is very simple, and the physical topology is only single-ended. So in practice, both of these factors mean that the bus can be very susceptible to external interference, especially during EMC tests. This table shows an overview of I²C specifications. For standard mode, where the max data rate is 100 kilobits per second, the maximum rise time is 100 nanoseconds, while the max bus capacitance is 400 picofarad, and the max current is 3 milliamps. On the other end, the high-speed mode operates with a max data rate of 3.4 megabits per second and a max rise time of 10 nanoseconds. Here, the max bus capacitance is 100 picofarad, and the max current is 3 milliamps. All ICs that participate in the I²C bus have open collector outputs. These switch the pull-up resistors alternately to reference ground, and then they generate the logical states, 1, which is VCC, and 0, which is GND. Now, as we saw in the original table, the maximum permissible edge rise times decrease as the data rate increases. The mathematical relationship of the min and max values for the pull-up resistors is seen in this equation. V sub CC is the reference voltage level of the I²C bus measured in volts. V sub L is the maximum logic 0 threshold level in volt. C sub bus is the maximum parasitic bus capacitance of the application measured in farad. T sub R is the max allowed rise time depending on the data rate measured in seconds. And I sub pull-up is the maximum possible current through the open collector pins in amps. The pull-up resistors, in combination with the parasitic bus capacitance, form an RC element. This leads to a delay of the edge rise time of the square signal. In many applications, this RC element is often the limiting factor regarding the maximum possible data rate and the cable length. Now, as shown in our original table, the I²C specification therefore results in a maximum bus capacitance of 400 picofarad at 3 milliamp current for the most commonly used data rates. The smaller the pull-up values are selected, the shorter the edge rise time can become. As can be seen in our equation, the lower limit determines the maximum logic low threshold, the voltage reference level, and the maximum possible current. The parasitic bus capacitance depends on a variety of things, including component capacitance, length and width of traces, approximately 0.5 picofarad per centimeters, length, type of cable and connectors, and also the layer structure and dielectric constant of the PCBs. Next, we'll discuss the selection of the filter and overvoltage protection components. To increase immunity to ESD, burst, and radiated RF, a combination of surface mount ferrites plus TVS diodes can be used. Wideband surface mount ferrites continuously build up impedance above 10 MHz and are therefore able to protect the bus against high-frequency interference. Overvoltages can also be effectively diverted to reference ground by the TVS diodes. Since the values of the pull-up resistors are often in the kiloohm range, the RDC, as well as the impedance of the surface mount ferrites below 10 MHz, only play a minor role here. This means that in a first consideration, it can be assumed that the edge rise time of the useful signal is hardly influenced in practice. But if you select suitable TVS diodes with low capacitance, their component capacitance also has no relative influence on the signal quality. During an ESD test, for example, a current of more than 10 amps can flow briefly, which then leaves a voltage of about 10 volts at this diode. All other ICs on the I²C bus must then withstand this same voltage. Now, this only works if a low impedance ground, such as a large copper area and an inner layer, is provided to avoid a further voltage drop. With the help of the free simulation program I²C, it's pretty easy to investigate the influence of the parasitic bus capacitance in combination with the selected pull-up resistors. Now, in order to generate that desired useful signals, it's advised to use a voltage-controlled switch. With the help of the voltage source, practically any periodic signal can be generated. So for this purpose, the pulse function is selected and the desired bandwidth is determined on the basis of the desired I²C specification. For the widely used 400 kilobits per second variant, a period duration of 2.5 microseconds is selected. For a 50% duty cycle, the high time is set to 1.25 microseconds. In order to determine the edge steepness of the signal, you need to get the rise times from the data sheets of the ICs being used on the bus. To be able to use the maximum allowed 400 picofarad parasitic bus capacitance, then the pull-ups were set to 1 kiloohm. 3 different channels were also simulated, including without parasitic bus capacitance, 400 picofarad parasitic bus capacitance, and 400 picofarad plus wideband multi-layer surface mount ferrite. The simulation result shows that practically no influence on the rise time of the signal can be expected from the multi-layer surface mount ferrite. Because each multi-layer surface mount ferrite also has an inductance component, then minor oscillations are visible in combination with the bus capacitance. However, these are not critical because their amplitudes are less than 10% of the actual useful signal. In the real measurements, these oscillations are significantly lower. In order to verify this relatively simple I²C simulation, we needed additional measurements, and these were taken and performed on a Worth Electronics Sensor BLE Featherwing kit. This kit consists of a master board, which contains the microcontroller. The other 2 contain a Worth Electronic Bluetooth module and some various Worth Electronic sensors, such as the 3-axis acceleration, temperature, humidity, and pressure. The master board communicates with the other 2 via the I²C bus at a maximum data rate of 400 kilobits per second. The sensor data can then be visualized with a suitable smartphone app, also known as the Worth Electronic or I²C-Sensor BLE. A parasitic capacitance of 400 picofarad with respect to GND was simulated using MLCCs. That same multi-layer surface mount ferrite was used in the simulation, plus a TVS diode array. Additionally, 20 centimeters of cable was used to connect the sensor board to the rest of the I²C. This arrangement can be seen in many applications in practice. During these measurements, the voltage curve on the SCL line was always measured. First, we have the reference measurement with 1 kiloohm pull-ups without further changes of the used feather wing hardware, which equals 46 nanoseconds rise time. Our next reference measurement is with 1 kiloohm pull-ups plus a multi-layer surface mount ferrite plus a TVS diode array, and also includes a 20 centimeter cable, giving us 46 nanoseconds rise time. Our final reference measurement is 1 kiloohm pull-ups plus multi-layer surface mount ferrite plus DVS diode array plus that 20 centimeters cable. Also included is a 400 picofarad MLCCs, which equals 344 nanoseconds rise time. These measurements show practically identical results to our simulation before. The rise time and the signal quality are not negatively affected by the multi-layer surface mount ferrite in combination with the TVS diode. The rise time of the high signal, which is critical for the timing, depends only on the bus capacitance in combination with the selected pull-up resistors. Using that smartphone app, the I²C BLE, error-free operation can be verified in all 3 tested scenarios. In this podcast, we were able to show by simulation and measurement that surface mount multi-layer ferrites in combination with ESD protection diodes practically do nothing to influence the data signal, or SDA, and the clock signal, the SCL, of the I² bus. The edge steepness of the signals is mostly influenced by the pull-up resistors in combination with a parasitic bus capacitance. In return, this component combination of ESD protection diode as well as broadband surface mount ferrite actually increases the noise immunity of the I²C bus. In practice, this means that a higher immunity to ESD, burst, and radiated RF. You can find the entire line of EMC components, ferrites, and TVS diodes available at Worth Electronic online. You can also order your very own Worth Electronic Featherwing Kit, available at we-online.com. For any questions, click the icon to talk with our live chat team 24/7. To view the materials and download this application note, visit www.we-online.com/appnote. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic tech specialists who will shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.